To introduce Amir Akbary. We're very happy that he's speaking for us. This is the last talk in this year's seminar. And we're very happy that Amir will be speaking for us from the University of Lethbridge. And he'll be speaking about Galois number fields with the fixed Polya index.
Thank you very much, Peyman, for the invitation and for introduction and for being so patient with me when I several times changed the time of the schedule of the lecture. Okay, so this is the joint work with Abbas Maruf-Parvar from University of Lethbridge. So Abbas is a PIMS postdoc at the university, and so he's actually working a lot on the Polya fields. And then so it was a good opportunity for me to learn about the Polya fields, and so we started this joint project together. So let me just start to introducing the main object of our talk. So K is a number field. CL of K is the class group of K, which is the quotient of the fractional ideals of K divided by the principal fractional ideals. And we have a specific ideal called the Ostrowski ideal. So we denote it by pi q of K. And this is basically the product of all the primes ideals of K that they have norm equal to Q. So this is called Ostrowski ideals. And using this concept now, we define the Polya-Ostrowski group. This is going to be a subgroup of the class group. So it's going to be generated by the class of all those Ostrowski ideals. So if Q is a prime power, so we have this PQK. And if Q is not a prime power, we don't have any prime of norm Q. In that case, we put pi QK as OK. And then the class of that is going to be basically the identity class. So to understand this best, let's see one example. Suppose you consider a quadratic field Q of root D and a prime P. So we know that actually this prime is going to decompose, and we have in K, and we have three possibilities. Either P is inert, P is split to P1 and P2, or P ramifies. So considering this, let's consider what is going to be pi P of K. So the only option that we have, the only ideal option that we have is the case of split in this case. So the Ostrowski class in this case become P1 times P2, which is going to be basically a principal ideal P. And so therefore, in this case, Ostrowski class is going to be trivial. Similarly, if P is inert, norm of P is going to be P squared. And in that case, the pi P squared is going to be, again, a principal ideal. And so therefore, the corresponding class become 1. The only case that we say something non-trivial is when P ramifies. So if P ramifies, then pi P squareds of K is going to be the class of P squared. And so therefore, square of P is going to be trivial. So therefore, P, the class of P, is going to be order 2. So as from here, we can see that actually the Polya group of a quadratic field is going to be a 2 subgroup. And in fact, we can say more. And this is something classical. Hilbert's theorem 105 and 106 give us exactly the cardinality of the Polya group. So to describe that, let's Sk be the number of ramified primes in Q of root D. And so the size of the Polya group is going to be the following. If D is less than 0, it's going to be 2 to the power Sk minus 1. If D is bigger than 0, this depends on the norm of the fundamental unit. If it's minus 1, it's going to be again 2 to the power Sk minus 1. And if the normal fundamental unit is 1, then we get 2 to the power Sk minus 2. For example, yes.
There's a question in the chat box. Are you fixing P or going through all the primes P?
We're going through all the primes P.
Going through all the primes. Thank you.
We're going through all the primes. Okay, so if D is minus 30, then Sk is going to be 3, and the size of POK is going to be 4. So here we have 3 ramified prime. So they get 2 to the power 2, we get 4. If d is equal to 10, then the normal fundamental unit is going to be -1. Again, in this case, we have two ramified primes, so we get 2. And then if d is 30, then the normal of the fundamental unit in this case is 1, and then we get 2 to the power 3 minus 2 in this case. And so therefore, again, we get 2. Okay, so there is a kind of another theorem that probably you're familiar with it, and that's the Gauss's genus theorem. So here I want to just compare these two together. So by the genus of K is going to be basically the two torsion part of the narrow class group. And the classical theorem of Gauss, it says that, although it's given in the language of the binary quadratic form, but in the modern language, it says that this two torsion part is going to be 2 to the power sk minus 1. So as you see, in many cases, these two are going to be coincides, but if you have a fundamental unit of norm 1, then these two things are not going to be the same. So you may ask that, okay, I'm talking about Gauss and Hilbert, and these are kind of much before Polya. How come Polya come to the picture? So let me tell you why we call this Polya group. So the reason is the following. So a number field K is called a Polya field if the Polya group of that number field be identity. And the reason for that is actually a theorem of Polya. What is actually special about the Polya field? If you consider the ring of integer valued polynomials in K of x, these are polynomials with the coefficient in K. So the ring of integer valued polynomial is going to be a Polya field if K has a regular basis. And by regular basis means an OK basis. The OK is the ring of integers of the number field, is a basis of polynomials in K of x such that for each n, Fn has degree n. So if such a basis exists for the ring of integer valued polynomial, we say that we have a Polya field. And examples of Polya fields are, for example, number fields of class number 1, or an imaginary quadratic field of odd class number is going to be a Polya field. Any cyclotomic field is going to be a Polya field. Easily we can see that for such a field, such a basis exists. Okay, so what's the reason for the Polya? I cannot actually, okay, I moved it. Why we call this one Polya? The reason is this classical theorem of Polya from 1990. So he proved that any integer valued polynomial in Q of x with coefficient in Q is going to be an integer linear combination of binomial coefficients. So if you consider binomial coefficient, it's going to be a polynomial of degree n, and it has the rational coefficient. But if you put any x there, you get an integer. And this beautiful theorem of Polya, in fact, is saying that any integer valued polynomial is going to be an integer linear combination of the binomial coefficient. In other words, the field Q has a regular basis. Okay? And in fact, Polya and Ostrowski, both of them, they consider this problem, this theorem is for the case of Q, they consider it over an algebraic number field. And for other algebraic number fields, also we have such a polynomial. I wrote one kind of simple one. You can easily check that if you consider Q of I and consider x times x minus 1 divided by 1 plus I, you get a Zi valued polynomial. So this is actually Polya's paper, appeared in Curly Journal in 1919, and the title is on integer valued polynomial in an algebraic number field. In the same issue of the journal, in fact, the paper after this one is a paper of Ostrowski with exactly the same title. And so both of these people, they study this problem. So this is kind of the reason that we call this one Polya field, Polya group, this subgroup of the class number class group. But actually today we are going to go to a different direction, and this is the type of problem that I want to discuss today. So we learned what is the Polya group, the subgroup of class group, and we want to see that in a given family of number fields, how often POK become as large as class group. So we can elaborate this a little bit more. Let's call the index of the Polya group inside the class group the Polya index. And we can ask this kind of more general question that in a given family of number fields K, how often for a fixed positive integer n, the Polya index become equal to T. So this is the type of problem that we are going to discuss. And let's first give kind of a general answer to these things. So first of all, we have evidence that probably there are lots of families that the Polya index is large as class group. There is a classical conjecture of Gauss that it says that there are infinitely many real quadratic fields of class number 1. We said that any class number 1 field, in fact, is going to be a Polya field. And in this case, Polya group is going to be identity. So trivially, actually, in this case, we have infinitely many possibilities. A number field of degree n is called an Sn field if its normal closure is isomorphic to Sn. And then there is a classical theorem of van der Waerden from 1934 that it says that in the set of reducible polynomials with integer coefficients of degree n and height less than or equal to h, the proportion of reducible polynomial having a Galois group isomorphic to Sn tends to 1 as h tends to infinity. So therefore, the density of irreducible polynomial with the Galois group Sn is basically 1. So randomly, if you have a irreducible polynomial, is going to have this property. And then we have the following more kind of recent theorem. The first one is due to Chabert and Halberstadt from 2020. So they proved that if K is an Sn field with n equal to 3 and n bigger than or equal to 5, then the Polya group is going to be the same as the class group. And just last year, Abbas Maruf-Parvar also considered the case of n equal to 4, and he could show that actually for the case, he could prove that in case of S4 field, also the Polya group is going to be big, is going to be equal to the whole class group. So if you combine this with the van der Waerden theorem, you could see that with probability 1 for any number field of degree n bigger than or equal to 3, POK is going to be equal to the class group. So this is a kind of a general probabilistic idea, and then we are not only consider the Galois extension, we consider all extension, Galois and non-Galois. So, but then again, I don't want to go to this direction. I want to go to the other direction. In fact, I want to present here some finiteness theorem for the number fields with Polya index 1. Specifically, I consider two families. So one is the family of CM number fields, and the other one is a family of quadratic fields of ratio bigger type. And I'm going to describe these two families. And I want to present some finiteness theorem in these families. So from now on, D, M, small m, n, m1, m2, and m3 denote positive square free integers, so I don't mention this again. A CM field, what is a CM field? Is going to be a totally complex quadratic extension of a totally real field. A good example to keep in mind is the imaginary quadratic field or imaginary biquadratic field, Q of root minus m, root minus n, or imaginary triquadratic field, root minus m1, root minus m2, root minus m3. So we can think about this as a kind of CM field. And the type of the theorem or result that we are going to discuss are the following. We can show that there are at most 66 imaginary quadratic fields with the POK equal to the CLK. So the class group is going to be the same as the Polya group. And the complete list of this 65 of such fields with D less than or equal to 1365 is given in the following table. So these are fields that they have class number 1, 2, 4, 8, or 16. For the case of imaginary biquadratic field, we can show that there are 57 of such imaginary biquadratic field with the Polya group equal to the class group. And again, the list of this is given in this table. Okay, so these are the type of result that I want to discuss for the CM field. And what is a Riccio-Degger type? So first of all, I define the Riccio-Degger type integer is going to be a square-free integer d in the form of L squared plus R, which R divides for L. So it's very simple. So for example, you consider L equal to 3. So 4 times 3 is 12. R divides 12. R can be positive or negative. So you consider the basically positive and negative divisors of 12. And then you add the 9, L squared 9, with this value of R. And then you pick the square free ones. And in this case, for example, I get the number 35 up to 25. Do we have infinitely many RD types integer? The answer is yes. There are theorems in analytic number theory says that there are infinitely many square-free numbers in the form of, for example, n squared plus 1. So those are all Riccio-Degger type. Another fact is that a notable unit of RD type is going to be given in this form. In many cases, actually, this is going to be a fundamental unit. And because of that, we can have a good bound on the regulator. Because we have this explicit fundamental unit, we can see that the regulator is going to be actually small. And that is going to play a very important role. So what we can show for the case of RD types, we can say that there are at most 270 real quadratic field Q root D of RD type, with at most one of which is bigger than 451,605, such that the Polya group is the same as the class group. And in fact, we can give the list of most of them, like all of them, except the one that probably is there. This is the complete list of it. And as you see here, the class group again is going to be, the class number is going to be 1, 2, 4, or 8. And you may wonder that why actually I describe this thing to like the class number 1 to 2 groups, class number 2 to 2 groups, and so on. So there is a reason for that that we are going to explain in the rest of the talk. Okay. So is there any question at the moment? So this is the type of problem that we want to discuss.
I mean, I'll ask a basic question. So you say at most so this is sort of like the ones that have you know the ones where the Polya group and the class group are the same, are among that list, but you don't know which ones actually are like that.
No, we know that all of them actually, this is the complete list of 269 of them. And for all of them, we know that POK equal to CLK for all of them. But maybe this list is not complete. Maybe there is one more.
Oh, maybe there's only one more. I see.
Maybe there is only one more.
I see.
Yeah.
Is that one more field related to Ziegel zeros?
Exactly.
Oh, okay.
Exactly. Yeah. Hello, Kumar.
I made it.
Okay. So how we actually come to this problem, as I mentioned at the beginning, Abbas was working on the Polya groups, and he's postdoc here. So I wanted to just search online, and I found this preprint by Etienne Emilien, which I think he was a PhD student, and he actually proposed this problem. And he proved that there are only finitely many abelian CM fields K, such that the Polya group is going to be the same as the class group. So that was kind of the original motivation that I asked Abbas, okay, let's look at this problem. But also this problem resemble a kind of more classical problem, which is the basically class number problem, which is vastly studied. So if you consider, if you denote h of minus d, the class number of q of root minus d, d here is positive, minus is the imaginary quadratic field. So in Article 303 of disquisition arithmetic, Gauss conjectured that there are only finitely many minus d such that h of minus t equal to t. And in fact, for t equal to 1 and 2, he gave this conjectural list. So this conjecture actually was proved, a series of theorem, but the final kind of step was done by Hilbron in 1934. He proved that actually h of minus d goes to infinity as d goes to infinity, which implies the Gauss's conjecture. Again, the same year, the same issue of journal, Chawla generalized this result. So Chawla's result is the following. Let us k be the number of ramified primes in K, then h of minus d divided by 2 to the power sk is going to go to infinity. And if you remember from the previous slide, 2 to the power sk minus 1, which is basically the denominator of this quotient, is going to be the two-torsion part of the class group. And so from here, we can see that there are only finitely many imaginary quadratic fields such that the index of the two-torsion part of the class group in the class group is going to be equal to a fixed t. So this is, in fact, the generalization of the case, the class number 1 problem. And in fact, this problem is related to another kind of famous problem in the number theory. In the same article 303, Gauss also conjecturally give the complete list of even discriminant of primitive binary quadratic forms with one class in each genus. And I haven't defined the genus properly. I just defined about the genus, but this is a class of binary quadratic forms and an equivalence relation on that. And the question was that when these two classes are going to be the same, and he gave actually this complete list, which is given, and a total of 65 of them. And again, these numbers are quite famous. There are some things that they call them convenient numbers, and they studied by Euler. So the conjecture of Gauss was not completely, still is open, but sort of settled. In 1973, Weinberger actually showed that there exists at most 66 imaginary fields K, such that the two-torsion part of the class group is going to be the same as the class group. And the complete list, in fact, is going to be the list of these 65 numbers. Probably there is one more of them there. These numbers are not exactly the numbers in the Gauss's list, because this is written in the language of the quadratic field. The other one is written in the language of quadratic form. But having this one, having this list, you can actually generate that one. There is another result that I want to mention, and this is due to Louboutin, one class in each genus for abelian CM field. In 1996, he proved that there are only finitely many abelian CM fields K, such that GK is going to be equal to HK. GK is going to be the genus class number of K. So at the moment, only for the quadratic number field, we said that this is going to be the size of the two-torsion part of the class group. But then there is a more kind of general concept of the genus number, which we are going to prove in the rest of the, which we are going to state in the rest of the talk. One other interesting result in 2000, Chang and Quan classified unconditionally for non-quadratic fields all abelian CM fields with one class in each genus. All of them that actually they have GK equal to HK. Okay, we're going to see that in our work, this classification is going to play an important role. But to describe actually our result, we need some notation. So let's consider the case of CM field. K is a CM field. dk is the absolute value of the discriminant of K. K plus is the maximal real subfield of K. Epsilon of K plus is the fundamental unit of K plus when K plus is a quadratic field. F is the quotient of the discriminant of K by the square of the discriminant of K squared. And HK minus is the relative class number, is the quotient of the class number of K by the class number of K plus. And we use, for the ramification index of a prime P in K over Q, EP of K over Q. So having all these things, this notation, this is the result that I would like to discuss today. So let K run through a family F of CM fields with solvable normal closures, such that the discriminant goes to infinity in this family. Then, for every epsilon bigger than 0, HK minus to the power epsilon divided by product of P of the ramification index. In part 1 of our problem, P are divisors of F. F was the quotient of the discriminant. So this quotient is going to go to infinity as dk goes to infinity. And the second part of the result is the following. If the degree of K over Q remains bounded for non-abelian elements of this family, then we can say something more. As dk goes to infinity over F, we can say that this quotient is going to go to infinity. Now, actually, we're going to put more prime in the denominator. So in the first part, we had only primes that are in F. Now we can put all the primes that we have in discriminant, all the ramified prime, in fact. And we can say that these results, both of these results are going to be effective if the degree of K over Q is bigger than or equal to 6. So what's the relation of this with the Polya group, the subject of our discussion? So the connection comes from this theorem of Xanthema from 1982, which actually give us a description of the Polya group. So let's K over Q be a finite Galois extension. This is a description only in the case of the Galois extension. So with the Galois group G, then the following sequence is going to be an exact sequence, which is in one side we have the first cohomology group of G with the coefficient in the units of K. In the middle we have the sum of over the Z over EP over the ramification index, and at the end here you have the Polya group. This is an exact sequence, so therefore the size of the Polya group is going to divide the product of the ramification index. And so I just remind you about the result. As you see in the second part here, we have this product. So if I put epsilon equal to 1, if I replace HK in HK minus by HK, make the numerator bigger, and also I put here the Polya group, so make actually the denominator smaller. So definitely the quotient is going to go to infinity. So as a corollary, we get the following. For every positive integer t, there are only finitely many abelian CM fields K, and only finitely many non-abelian solvable Galois CM fields K of bounded degree with Polya index equal to t. So we can have this finiteness result, which comes from that kind of more general theorem. Okay, so now I think it's a good time to define the genus. So this was kind of the general theorem. If you remember in the beginning of the talk, I give a list that, okay, so for example, for biquadratic field, this is the list of fields that, imaginary biquadratic fields, this is the list that GK is equal to HK. sorry, not GK equal to HK. Size of the Polya group is going to be equal to HK. And how did we get that list? We actually explored the relationship between the size of the Polya group and the genus number. And so to do that, let's first define what is the genus number or genus class number. So for a number field K, the genus field gamma K of K is the maximal abelian extension of K, which is a composite of an abelian number field K star with K, and is unramified at all places of K. So it's something very similar, genus field similar to the Hilbert class field, but we have an extra condition. So we are talking about those abelian extensions that are the composite of K and another finite abelian extension, we call it K star. So as we see here, gamma K is going to be a subgroup of a subfield of the Hilbert class field. And the degree of the extension gamma K over K is called GK. And so from here, we can see that the GK is going to be a divisor of HK. So this is the genus field and the genus class number. And then we have a genus class number formula. So it's a result of Leopold, which is more general, but I wrote it here for the abelian CM field. The genus class number, GK, is going to be the product of the ramification index EP divided by the degree of the group, the degree of the extension. And so as you see, this product of the ramification index appear here, which appeared also in the Xanthema exact sequence. So in the Xanthema exact sequence, the product was equal to the size of the Polya group times the size of the first cohomology group of G and UK. So if you replace the product of the ramification index in the Leopold formula, we get the Polya class number formula. And there is a relation between the size of the Polya group for the abelian CM field and the genus number. So basically, if we can compute these cohomology groups, the degree of the extensions are kind of given most of the time. So therefore, we can see that what's the relation. And in some cases, actually, we can do that. For example, for a cyclic CM field, we can show that actually POK is going to be equal to GK because that cohomology group is going to be equal to the degree of extension. Also, for an imaginary biquadratic field K, we can compute that cohomology group, size of the cohomology group there, and we can get this result that POK is going to be either GK over 2 or it's going to be GK, the same as the genus number. And it's going to be GK over 2 only if the norm of the fundamental unit and the Hasse unit index, both of them at the same time be 1. For the imaginary triquadratic field, we can say something. So let's K be this imaginary triquadratic field. And let's consider K1, K2, and K3 are the 3 real subfields of this field. And we say that K is going to be type A if at least one of the fundamental units of K1 and K2 and K3 has norm 1. So not all of this real subfield, they have fundamental unit -1. So if we have this condition, we can compute that cohomology group. And we can actually show that for an imaginary triquadratic field K of type A, the size of the Polya group is going to divide the genus number. And remember, the genus number is going to divide HK. So if you want to, for example, study when POK become HK, we see that if such a things happen, for sure GK become equal to HK. So in other words, the observation here is that in many cases, or at least in these 3 cases that I mentioned, if K is a cyclic CM field, or is an imaginary biquadratic field, or is an imaginary triquadratic field of type A, then the size of POK is going to be the same as HK. This is going to imply that actually GK is going to be equal to HK. In other words, our problem, size of POK equal to HK, become a subproblem of one class in each genus, which is a classical problem. And as I said, is studied, and in year 2000, Chang and Kwon, or Kohn, they classified all abelian CM field that they have one class in each genus. So we use their classification, and use of their classification, we can report the following. So in the family of abelian CM field, the following assertion hold: there are 65 imaginary quadratic fields with possibly only one more value d, such that POK is going to be equal to the CLK. There are 57 imaginary biquadratic fields K with the Polya class number equal to the class number. 16 imaginary triquadratic field of type A with this property, and there are 77 non-quadratic cyclic CM fields with the property that the Polya group is going to be the same as the class group. Again, using the classification that by Chang and Kohn, this is going to be a list of the 65 of such field for the case of imaginary quadratic field. There is possibly there is one more here that we don't know. That's an open conjecture. The complete list of 57 imaginary biquadratic field extracted from there is going to be the following. And then the 16 imaginary triquadratic fields with the property POK equal to CLK is going to be the following. All of them, in fact, in this case, they have class number 1. Okay, so that's kind of the first type of result that I wanted to report. So how much payment, how much time do I have?
Well, Amir, we started a little late, right? So I think you have maybe around, I would say, yeah, 15 to 20 minutes. Something like that.
Okay, so that's good. So I can maybe slow down a little bit. And so just recap that we define the Polya group, and then we pose the problem when POK equal to the class group. This is a subgroup of the class group. And then we consider the case of abelian CM field and CM field basically, and establish some or report some finiteness results. There are finitely many K with this property. Okay, and relating this with the genus class number and the work that people did in the more classical problem of one class in a genus, we could come up with this classification. Okay, and now the other kind of family that we studied. So just let's set up our notation: K, CLK, HK, GK, as we defined it before. DK is going to be the absolute value of the discriminant of K. Again, we defined it before. RK, a new player here, is the regulator of K. And then we have the narrow class group, which is going to be the quotient of Fk by P plus of K. So this is going to be the principal ideals that they have a totally positive generator. So that's going to be P plus. And the size of CL plus is going to be the narrow class number. And similarly, we can define, considering the CL plus, we can consider GK plus, which is going to be the narrow genus class number. And the second type of the theorem that we have is the following. So let F be a family of Galois number fields, which the discriminant goes to infinity over this family. And let's assume the following two properties. Suppose that the degree of K over Q on this family be little o of log of the discriminant. Also the log of regulator be the little o of log of discriminant. Then we can have this Chawla type result again. HK to the power epsilon divides the product of ramification index. In this family is going to go to infinity. And probably you can guess that this is coming kind of as a straightforward application of the Siegel-Brouwer theorem. This condition, the degrees equal to little o of log decay, in fact, is part of that theorem, the Brouwer-Siegel theorem. And then the second condition that we imposed allow us that actually we get a good lower bound for the class number. Okay, is there any kind of family that we can apply such a theorem on that? The answer is yes. If you consider the RD types, the family of the real quadratic field Q of root D, which D is an RD type number. So this is a square-free number in the form of L squared plus R, which R divided by 4L. We can show that in this case, the regulator is small, is less than log of 3 dk. And so therefore, log of a regulator is going to be the little o of log of decay in this case. And so therefore, we can apply our general theorem, and we have the following this proposition. Here, because the whole thing is based on the Brouwer-Siegel theorem, the result is not going to be effective. But as a corollary, we can have this non-effective result. We can say that there are only finitely many real quadratic fields of RD type with the given Polya index CLK, the Polya index, Polya index. Yeah. Okay. One more thing before actually I present more kind of a more specific result, and this is a general observation that we had. We showed that for a real quadratic field, this result is not only for RD type, for any real quadratic field. We can show that the index of the Polya group in the class group is going to be the same as the index of the genus group in the narrow class group, the narrow genus group in the narrow class group. So in other words, for the real quadratic field, the problem that we are studying, in fact, become exactly equivalent to the classical problem of one class in each genus. So that's another thing. And now we can have this result. There are at most 270 real quadratic fields Q root D of RD type, with at most one with D bigger than or equal to 451,605, such that the Polya group is going to be the same as the class group. Again, because our result is not completely effective, we cannot have a unconditional lower bound for the class number in this case. And so therefore, there is possible that there is one more D, which is not in this list. So this is the list of, almost complete list of the class, the quadratic field of RD type, with at most one exception for which the size of the Polya group is the same as the class number. Okay. And actually now I can tell you that what was the reason that we divide all the class number one into two groups. The reason is that, as you see, POK equal to HK, for both of them, the class group, the class number is going to be 1. But if you consider the problem of GK plus equal to HK plus, for some of them, the narrow class number is going to be 1, and for the rest of them, the narrow class number is going to be 2. So although the index of the same, and therefore the classification is going to be the same, these two problems are equivalent, but then HK and HK plus are not all the time the same. Okay, and so therefore this is also give us the list of the complete RD types, with at most one exception for which the narrow genus number is the same as the narrow class number. Okay, is there any question?
May I ask just one question?
Yes, please.
Yeah. So about this, I the type when you make this very nice theorem, then you are using this explicit version, right, about this unit, probably that. And can you prove that? And you told that in most cases it is fundamental unit, but in some cases perhaps not. So how do you estimate the regulator in these cases when perhaps it is not fundamental unit?
So the main result that is going to come to the picture is that we know this explicit as estimation of Rk less than log of 3dk. So the fact that actually everything here is explicit allows us that actually do the computation.
Oh, I see.
Yeah. So basically, it's going to be the one way you can think about this is hk divided by this product that we have. So it is something like n divides by the number of divisors. It's like n divided by tau of n. And then we know that the tau of n, in fact, is going to be the little o of n to the power epsilon. And we can make everything explicit there. So this is actually exactly the same idea. But the part that is going to play a very important role is that we need explicit lower bound for hk there. And then that one is kind of, if you use the Brouwer-Ziegel theorem, is going to come in terms of Rk. And so, and in general, we don't know actually how big it's going to be Rk. In fact, Rk is huge usually. But in this family, the Rk is very small. And also we have this explicit bound. So therefore, that's the same way that actually we can, for example, establish the number of divisors is going to be less than or equal to something explicit times n to the power epsilon, but some explicit, we can make everything explicit there. Similarly, we can do the same thing here too.
So thank you.
Okay, thank you. Okay, so let me just finish off with saying that how we can prove this kind of general theorem. Not the numerical one, the general theorem. I try to explain this for the case of CM field. So there are two ingredients. So one is the lower bounds for the class numbers. And so the other one is the sufficient condition for divergence to infinity of the multiplicative function, which is this second ingredient is very related to this discussion that just we had a few minutes ago, like just right now, about this divisor function. Because if you look at the proof of the fact that tau of n is little o of n to the power epsilon, this sufficient condition is going to come to the picture. Okay, so first, lower bounds for the relative class numbers. These are known. For the abelian CM fields, Louboutin actually give this bound. These bounds are not optimal in any way. So if we have dk to kind of any power less than 1, things are going to work very nicely. And so I just put a number there. I didn't try to put them optimal. And the second ones are for the CM field with solvable normal closure. And this type of bound actually was developed for the first time by Kumar Murthy, which he considered these bounds for HK. And more recently, following his method, Penji Wang, in fact, has these bounds for the relative class number. So for a CM field with solvable normal closure, if the degree is 4, there is a non-effective constant such that the HK minus is going to be bounded by dk to the power 1/12. And then we have two other type of bounds for n bigger than or equal to 6. So the first one is going to give us HK minus bigger than or equal to Cn times f to the power 1/3. F is just part of the discriminant, is not the whole discriminant. But the feature that we are here, we have that these Cn's are going to go to infinity. These constants are going to go to infinity as n goes to infinity. So that's one type is like that. And the second type, that here we have the discriminant decay to a power, we have this constant. Now these constants are going to go to 0. So the result comes as a kind of playing with these two. Actually, all of these bounds that are already established in the literature. And this lemma, which is an elementary lemma. So if f is a multiplicative arithmetic function, which satisfying this property that f of p to the power m goes to infinity as p to the power n goes to infinity, then we can say that f of n goes to infinity. Okay, so the proof comes something like this. Like, let's consider the case that the degree is bigger than or equal to 6. So we write decay as a product of prime divising decay discriminant with the exponent np. There is a relation between the exponents that appear in the discriminant and the ramification index. The ramification index are bounded by those exponents, ep less than or equal to 2np. And then for epsilon bigger than 0 and n bigger than or equal to 0, we are going to use our first bound and see when this quotient is going to be less than n. So we use our third bound here, and then we get this lower bound. And as I said, Cn is going to go to infinity as n goes to infinity. So from here, if you fix this n, we can see that there's only finitely many n that satisfy this property. So now for those n, which is going to be the number of them is going to be finite, we're going to use the second, the last bound, which is now for the last bound. We can say that this c tilde n is going to be bounded. And now if the discriminant goes to infinity, we can use our lemma, elementary lemma. Each component here is going to go to infinity when we're considering over just the primes. So therefore, the product is going to go to infinity. So if this product wants to be less than m, there are only finitely many decay that is going to satisfy here. And then we know that correspond to finitely many decay, we're going to get finitely many k. So therefore, that's going to establish our result. And again, this proof model exactly two things. One is the Kumar-Murthy's proof that he proved such a result for the case of CM field with solvable normal closure, and also that elementary result that I say, which is tau n is going to be the little o of n to the power epsilon, which is written, for example, in Hardy and Wright, and uses that lemma. So we can put this product in the denominator, and we can decompose it and apply that lemma because of the combination of these two things. I think that's all I wanted to report today. Thank you very much for your attention.
Thank you.